Okay, so today we're talking about using the graphical tools that you have in MATLAB to make graphics that you can just drop into the papers that you're preparing to send to an IEEE publication, transactions, a conference, a journal. How can you use MATLAB to just spit out graphics that are going to drop into that paper and look clean, polished, neat, professional? I'm going to give you today the 3 principles that you need to do that. Principle number 1. We are going to have consistent figure sizes. We're going to think like designers. When you're designing a graphic that goes into a paper, we're going to think in terms of the print dimensions of that graphic. So we know how much text that we can fit in there. We know how to make it consistent with every other graphic in that paper. Number 2, we are going to make sure that our text is consistent and is legible. We don't want a text too small. We don't want it too big. We want it the same size everywhere. So we're going to take control of that. Number 3, we're going to do it in a way that's repeatable. There's nothing worse. You've been working on a paper full of graphics that you've hand rolled, you've hand made them, you've hand saved them, and then suddenly your supervisor says, hey, can you change that parameter value? Can you change that color? And you're back taking weeks to get the thing together again. No, we want something where you can just run your code base, hit F5, it's going to spit out a load of graphics, and you can drop them straight into your paper. Those are our 3 principles. So how are we going to make this work? Right. Well, the key thing here is this number, 8.89 centimeters, okay? Because if we look at a paper, this paper mine I wrote a few years back with a colleague, if we look at a paper, and it's an IEEE paper, the consistent thing is that anywhere I go, that's going to be 8.89 centimeters wide, okay? So any block of text that I select, this column is physically going to print out at 8.89 centimeters, and that is super important. That's the key dimension that determines everything. Same over here. Our columns are 8.89 centimeters wide. So that means our figures are going to drop into that column and they need to respect that width. They need to be designed with that print dimension in mind, okay? So this figure here, if I just look at that one pane of it, part C, that's going to be 8.89 centimeters wide. And I designed it to be 8.89 centimeters wide using these principles. So we can see here, all those 3 vertical axes, they line up. We can see that the height of pane A is the same as the height of pane B. Okay, we can see that we've got these matched axes. So 9:30 in the morning is the same here as the same here. Our text is the same size. Our text is the same size. So everything's neat, everything's tidy because we've insisted on making it consistent. So how do we do that? So let's just have a look at the MATLAB code. Okay, the first thing that we need here, the first thing we need to insist on is we have a separate script where we prepare our data to where we visualize our data, okay? So this is just a placeholder, okay? So this is where I'm a power engineer. You might do some load flow simulations. Maybe it's an optimization. Maybe you're taking data in from a lab device. Whatever you're doing, it could be 10,000 lines of code, okay? Here, I just have these, these notional little sample, few lines of code to generate these 2 variables, voltage and time. Okay, the crucial thing is once I'm done creating my data, I need to save that out of my workspace to a .mat file. Okay, so that's what the magic here is. Line 16 is going to take all that data that I've created and it's going to save it. I'm going even further in that I'm going to make sure my file name takes in this time. Okay, so that then I can come and say I ran the script on this date and time and I got this output. So once I've published that paper, maybe I'm going to share that output on a repository like Zenodo or Figshare, an institutional repository, okay? This is about transparency, it's about replicable science. So I can just go like this, run those through, hit F9, and here we have a look. There's my new .mat file that just got created, okay? So I've prepared my data, I've created a .mat file. Let's just copy the name of that. We come back here. Now, I want to visualize the data, okay? You can actually see this is a much larger script. So the first thing we're going to do is we're going to load up whichever data file we want, okay? So we're actually going to start from a blank slate. We're going to clear our workspace and we're going to load up that data file, okay? So we're completely separating the creation of our data and the visualization of our data. So maybe if you're doing a PhD, you might come back in a few years' time and decide you're going to recreate your graphics to go into your thesis with a different style. That's no problem. You're just loading up the data and creating the graphics, okay? So, but today we're creating the graphics for an IEEE paper. So that means we're going to set up some things that are normal, okay? So we're going to make sure, I've just run it there, we're going to make sure its default text size is going to be 8 point Times New Roman. We're going to have a white background on our figures, and we're going to be using the text interpreter so we can actually put like mathematical notation into our graphics. Okay, so we're going to make a figure, and we're going to build it up piece by piece. Everything here is about how we build up this figure piece by piece to do everything in code, so you're not doing anything by hand, and everything is repeatable, okay? So first thing is, let's make the figure, set it into centimeter units, and set the size of it, okay? So let's run that, and here's my figure, okay? There's my figure, and the magic is, we have determined that its width is going to be 8.89 centimeters, okay? So everything we're doing as we build this figure, right, as we work through this script, everything is respecting that we're working in a frame that's 8.89 centimeters. So if I tried to put in, because I've said I'm working in 8 point times New Roman, so if I try and add in an axis label that says supercalifragilisticexpialidocious, and that's not going to fit within 8.89 centimeters, I'm going to see it's going to run off the end, okay? So that's how we do it. We set the position. So this is where it starts in the bottom left down at the origin, and then this determines the horizontal width, and this determines the height. The height is actually something I have a bit more freedom about. If I have got more room in my paper and I've got a more generous page count, I can make them taller, okay? So I can decide how tall or how short my graphics are. I can't do anything about the width, okay? So the height is a free variable, the width is fixed, okay? My advice to you would be to keep that height consistent, okay? Right to your paper, it's just going to look a little bit neater, okay? So the notional data I've created, I'm saying it's time series data of a voltage, okay? That's what I'm pretending is going to happen here. So I'm going to plot that as a stairs plot, okay? So let's just run that, and up pops our stairs plot over here. So that's MATLAB has just automatically set up a figure, okay, as a stairs plot, which is fine. For exploratory data analysis, I can look at that figure, I can learn something, but it's not good enough to go into a publication. To put it into a publication, I have to work through every design detail and decide whether I'm happy with that or not, okay? So we've done our stairs plot. Again, it's a stairs plot because I only have data for these 48 hours, okay? So I'm not even going to interpolate between them. That's why it's flat and up and flat and up. A stairs plot is appropriate for this. Okay, so let's decide the axis limits. This is super important. Let's run that. You can see what happens. I've said I want my axis to run from 0 to 48 horizontally. We can see that there. And from 18 to 22 vertically. This data is time and it's kilovolts, okay? So as the engineer, okay, as the person who understands this data, I'm going to decide about those axis limits. MATLAB on its own has no ability to do that, okay? I'm the expert. I have the context, so I'm going to determine those axis limits. Okay, then these tick mark locations, okay? So currently I have on my y-axis, my vertical axis, I have tick marks at 18, 19, 20, 21, and 22. Okay, because MATLAB automatically generated that. But I have the context. I'm going to run this here, and I'm going to change those tick marks. So I'm going to put it in at 18 and 22, because I know that's the upper and lower range, let's say, for a voltage, you know, on this buzz bar, let's say. 20 is the nominal voltage, and it's in the midpoint, so that's a sensible thing to include in there. But let's say I know that there's an undervoltage limit of 19.2 kV and an overvoltage limit of 22.25 kV. Okay, it's my axis. I get to decide where the ticks should go. So I'm going to put those ticks in. They don't have to be symmetrical. Now, I'm going to label those tick marks in a way that's legible. Okay, so I'm actually going to put the unit in on those tick mark labels. So this string, we can see it's a string because it's enclosed in those single quote marks. This one corresponds to this tick mark. This tick mark at 19.2 kV, the string for that is going to be vmin, and we're using the LaTeX terminology here to get the lower case, so it's going to be vmin, and we can see that come in here. It looks great. So there's our vertical axis. We're showing voltage now in a sensible way. Okay, now my time axis, 48. It's 48 hours over the course. It's 2 days, right? So I'm measuring some voltage data over 2 days. It's just notional data. Okay, so that looks awful. 0, 10, 20, 30, 40. That's got nothing to do with time. Okay, I hate to see that in a paper. You understand the units. It's your data. You're the analyst. So you need to impose a sensible way of showing that. Show time as time, okay? So let's put in tick marks every 8 hours. Okay, that's a good start, okay? But because it's time, let's show it as time, okay? So we're going to use these wall clock units, 24-hour clock style, military style. So instead of saying 16 hours after midnight, we're going to show that as 1600 hours, okay? Because that's going to tell the viewer, when you see that, we're talking about time. Okay, Midnight, 8 in the morning, breakfast time. 4 in the afternoon, okay, time to be finishing up work, okay? It hits, it's intuitive, it makes me think of time, clocks on a wall, okay? So I'm very careful with the ranges of my axes. I'm very careful of where I put the tick marks. I'm very careful of how I label those tick marks. Okay, now, earlier on, right up here, we determined the position of this figure, okay, was going to be 8.89 centimeters wide by 4 centimeters high, okay? So the entirety of this from here to here is going to be 8.89 centimeters, okay? But what about the axes within that? So the axes are these, right? That's my vertical axis there. This is my horizontal axis here, okay? So the origin of my axes, where am I going to put that, okay? So how do I position that plotting area, the axes within the frame? That's what we're going to do here, okay? So we're going to work in centimeters, and we're going to position it like so, okay? So see how it moves over. So what we've done is we've said it's going to be 2 centimeters in from the left and 0.9 centimeters up from the bottom, okay? So this position here, in from the left, that little gutter where we're going to put our title on our vertical axis, we've decided that's going to be 2 centimeters, okay? And we've decided this is going to be just a little less than 0.9 centimeters. Then we said that the width of the axis is going to be 6.5, okay? So from here over to here is going to be 6.5 centimeters, okay? So that just about leaves room for that last little tick mark label, okay? An IEEE column is tight. 8.89 centimeters isn't that much. So we need to be very deliberate and careful that we're getting every bit of use we can out of our very limited plotting real estate, okay? So again, it's a good practice for the different graphics in your paper that if you leave that inset of 2 centimeters consistent, that means all the vertical axes are going to line up. That's neat, it's tidy, it's consistent. Okay, another next step here, we're going to take the box off. See what we do here, okay? So the outer extra box, we don't need it. It's wasted ink, it's wasted pixels, it's distracting, it's cluttery. Let's get rid of it. Okay, now let's put in our labels, okay? So we've made room to put in our axis labels, okay? So I'm going to put in a Y label here. I'm going to do it in, I've set up my default is Times New Roman, 8 point, and I'm going to do it in bold, just so it pops a little bit as an axis label. And I'm setting it up so I want to do it across multiple lines. So I've built a little cell array here. So we can have line 1, line 2, line 3, line 4. So let's see what we get when we run that, okay? So by default, MATLAB rotates your axis labels. I don't like that. So we've got a line here to derotate that. We find that axis label, we put the rotation back to 0, and now it sits up like that, okay? Rotated axis labels, they make you do this with your head to read it. No good, right? Let's make enough room. We've got our 2 centimeters of a gutter or an inset where we're going to put an axis label that's set in the normal dimensions, left to right, simple text that we can read, okay? I'm using a Unicode arrow here, and so again, it's just going to direct the eye up and down that axis so people know that's what's going on, okay? Going to do the same thing here for our x-axis. In it pops time. Now I don't need to split it across multiple lines, like 1, 2, 3, 4 lines for the vertical axis, just 1 line for the horizontal axis. That's going to be a common pattern, okay? Time, and again, we're just using that little arrow just to draw the eye, okay? And we've made just enough room in our gutter so that horizontal axis label sits neatly and the vertical axis label sits neatly. We're not wasting space. We're not squeezing something in, okay? And we're doing that in a consistent way. So with our frame, which is 8.89 centimeters wide and 4 centimeters high, we're in a very deliberate way. We're filling that with the graphical content that we want to be there. Okay, so now looking at that, I think that's going to be a nice graphic, okay? I'm now ready to put that into my paper. So again, we're going to prepare a file name. So every time we generate graphics, we have them timestamped. We know when they came from. So if we're sharing our data after the fact, if anyone's interested in where it all came from, we're documenting our progress. Now, here's something magic. Export Fig. I actually have this up here as a dependency. You need to get this off MathWorks. It should have been built into MATLAB. It isn't, okay? This is going to take this beautiful figure we've made over here and it's going to spit it out as a very, very high resolution PNG file. We specified here it's a PNG file, so it's going to spit it out. M3 is going to really give us a lot of resolution and it's going to spit that out as a PNG file. So let's just run that and see what we get. And here's our file that we just spat out. So here's our nice PNG file. We can zoom all the way in and it doesn't get too grainy. Okay, some people are going to want to use vector graphics. and there's reasons to do that. Today we're going to be working raster style, okay? So now, how do I drop that into my paper, okay? We'll copy that. I'm working in Overleaf over here. I have it synced with my Dropbox. So I'm going to drop that file into my Overleaf project directory. Not everyone will be working in Overleaf, but if you are, or in any LaTeX distribution, it's going to be something very similar. So I've already got one figure here, and now I've got a new figure that I'm going to drop in here. And we're just going to compile this and see what we're going to get. So I used the same script, very similar script, to produce the first figure as I produced the second figure. So bus 1 voltage, it looks very, very similar to bus 2 voltage. I've got two beautiful graphs. They're consistent, they're tidy, they show different data, but they do it in a consistent way. And we can see that the text in here matches the size of this text matches the size of the caption. It's consistent with what we have in the rest of the paper. So that's how we do it, okay? So this is a repeatable workflow in MATLAB. We produce our data in one place. We open up that data to visualize it. When we're visualizing it, we control the width, we control the text size, we take ownership of the axes, we remove clutter, and we save it out automatically as a PNG file. So there's no human intervention required. I can just run that script, I get my graphic, and I drop it straight into my paper. So that's how I do it. Hope you learned something. Thank you so much.